our channel.
I'm Estella.
And I'm Aditi.
We both got 5s in AP Chem and will hopefully help you to do the same.
Today, we're going to be talking about electron configuration and electromagnetic spectrum.
Button your lab coats, tighten your goggles, and let's get started.
This is a Bohr diagram. No, not that type of Bohr.
Although it may seem boring, it's actually useful.
Bohr was this old guy who made this diagram to illustrate where electrons are likely to be found in an atom.
As you know, atoms are composed of protons and neutrons in the nucleus, and electrons in surrounding orbitals. This diagram shows the different shells and the distance of those shells from the nucleus. Different shells can hold different amounts of electrons.
Yes, electron configuration is when we write out the distribution of electrons across those orbitals. Here is a more detailed diagram that better illustrates this concept, called an orbital diagram. Each line is an orbital, which can hold 2 electrons. These electrons each have a spin, shown through arrows. Each shell has a different amount of orbitals and subshells.
This is the 1s, 2s, and 2p, which consist of 3 orbitals. Going on to the 3rd subshell, however, there is 3s and 3p, but an additional subshell appears.
This is the d subshell, which has 5 orbitals and can hold 10 electrons. However, this is written after the 4s subshell because the 4s subshell is filled first.
Let's draw out nitrogen's orbital diagram ourselves. The lowest orbital, or the one closest to the nucleus, is filled first. This is the Aufbau principle. This is because the positive charge of the nucleus attracts the negative electrons.
Next is Hund's rule. Electrons will fill each orbital with 1 electron first, before they double up, as seen with the nitrogen example. And these electrons will have the same spin.
Finally, the Pauli exclusion principle states that each orbital can only hold 2 electrons, and they must have opposite spins.
Now we're ready to draw nitrogen's diagram.
Nitrogen has 7 electrons, so keeping in mind our rules, we fill in 1s first.
Next is 2s, and then 2p. Remember, fill each orbital with 1 electron first, then double them up with opposite spins.
Yay! We did it!
Now let's talk about light.
These aren't fixed positions. When electrons have enough energy, they can move to higher energy levels and later fall back down to their original position, emitting a photon, which is a particle of light. These photons each have a different wavelength depending on the energy emitted, which depends on how far the electron falls.
And wavelength is inversely related to frequency, which is directly related to energy. Here are the equations that show this relationship.
Here's a practice problem. Try it on your own, and we'll explain it. What is the energy of a photon with a wavelength of 630 nanometers?
Remember, the speed of light is in meters per second, so convert wavelength to meters first.
Then, divide the speed of light by the wavelength in order to get the frequency in 1 over s.
Then, multiply the frequency you found by Planck's constant, 6.626 times 10 to the negative 34, in order to find the energy in joules.
Doing this, we get 3.16 times 10 to the power of negative 19 joules.
Hold up. This is kind of confusing. Can I get a recap?
No, but you can get a rewrap.
Electron config? My brain is so big. 1s2, 2s2. Now you know just what to do. Photons and light, oh, what a sight. Electrons jumping around, their wavelengths shall be found.
Waka waka.